Every moment, with every breath and touch, we are in constant interaction with atoms. Yet their true nature remains shrouded in mystery. Join us as we journey to decode the mysteries of the atomic world, where we will seek answers to fundamental truths of everything we see, touch, and experience. An atom is the smallest unit of ordinary matter that forms chemical elements. Every solid, liquid, gas, and plasma is composed of neutral or ionized atoms. At the heart of every atom is the nucleus, which is tightly packed with two main types of particles, protons and neutrons. The protons carry a positive electric charge, while neutrons are neutral and have no charge. Surrounding the nucleus are electrons, tiny particles compared to protons or neutrons, which orbit the nucleus at various energy levels, known as electron shells. These electrons hold a negative charge and are crucial in the bonding between atoms, which occurs when atoms share or exchange electrons to fill these shells, seeking stability. Interestingly, despite the central role these particles play, most of an atom's structure is actually empty space. If you were to imagine the nucleus as a peanut sitting in the center of a sports stadium, the electrons would be like tiny flies buzzing around the stands, with vast distances between them and the nucleus. This structure of the atom not only defines the identity of the chemical element, via the number of protons in the nucleus, known as the atomic number, but also its properties and the way it will interact with other atoms. Building on our understanding of the atom, modern science provides a more nuanced definition that goes beyond the basic model of protons, neutrons, and electrons. Today, atoms are recognized not only as the smallest units that retain the properties of an element, but also as entities capable of joining together in countless ways to form everything from the air we breathe to the materials used in cutting-edge technology. The modern view of the atom emphasizes the quantum mechanical nature of these particles. Electrons, for example, do not travel in fixed orbits around the nucleus as once thought, but rather exist in cloud-like regions called orbitals, where each electron's position is described in terms of probabilities rather than definite paths. This quantum perspective allows scientists to predict the behavior of atoms in complex chemical reactions and even in the sophisticated materials used in electronics and medicine. Additionally, the number of protons in the nucleus, the atomic number, still determines the type of element an atom represents, but isotopes, atoms with the same number of protons but different numbers of neutrons, demonstrate that atomic mass can vary within a single element, leading to subtly different physical properties. This refined understanding also supports why some elements are radioactive and others are stable, influencing everything from geological dating methods to nuclear energy production. The historical origin of the concept of the atom dates back to ancient times, particularly to the philosophers of Greece. Around the 5th century BCE, a philosopher named Democritus proposed that everything in the universe is made up of tiny, indestructible units he called atomos, meaning uncuttable in Greek. This idea was revolutionary because it suggested that the changes we see in matter are not due to changes in the fundamental substances themselves, but in the way these substances are arranged and combined. Democritus theorized that these atoms exist in various shapes and sizes, and their interactions determine the properties of the materials they compose. Although Democritus's ideas were largely based on reasoning rather than empirical evidence, they laid the groundwork for future scientific inquiry. For centuries, the concept of atoms was more philosophical than scientific, as there were no experimental methods available to test the theory. It wasn't until the early 19th century that John Dalton, an English chemist, revived and refined the concept based on his experiments with chemical reactions. Dalton proposed that each chemical element is composed of a unique type of atom, and that chemical reactions involve the rearrangement of these atoms. Dalton's atomic theory marked a turning point, transforming the atom from a philosophical concept to a scientific one. His work provided the first meaningful insights into the behavior of matter at its most fundamental level, setting the stage for the development of modern chemistry and physics. Over the ensuing decades, further research would not only confirm the existence of atoms, but also reveal the complex internal structures involving protons, neutrons, and electrons, expanding our understanding far beyond Dalton's initial theories and bringing us into the realm of quantum mechanics that defines much of modern science. This journey from ancient speculation to contemporary science underscores how persistent curiosity and rigorous investigation can dramatically expand our understanding of the natural world. The Big Bang theory emerges as a pivotal scientific explanation for the origin of the universe itself. This theory posits that the universe began from an extremely hot and dense state approximately 13.8 billion years ago and has been expanding ever since. It was first proposed based on observations that distant galaxies are moving away from us in all directions, suggesting that the fabric of the universe itself is stretching. The Big Bang theory is supported by several key pieces of evidence: the redshift of galaxies increasing with distance, which indicates that the universe is still expanding; the cosmic microwave background radiation, which is the afterglow of the initial explosion, now cooled and spread thinly across the universe, observable as a faint microwave signal omnipresent in the sky; and the relative proportions of elements like hydrogen and helium, which match predictions derived from the theory. Understanding the Big Bang theory helps us frame questions about what preceded that moment and the ultimate fate of the universe. It ties together the atomic elements we discussed earlier, as the intense heat of the early universe was responsible for the formation of the simplest atoms like hydrogen and helium during a period called nucleosynthesis. These atoms later clumped under gravity to form stars and galaxies, initiating the cosmic evolution that has led to the current complexity of the cosmos. Building on our understanding of the Big Bang theory as a pivotal explanation for the universe's beginnings, this concept tells us that the universe started from an incredibly small, hot, and dense point approximately 13.8 billion years ago. This event, often described as a singularity, marks the inception of both space and time, dictated by a set of physical conditions that current physics can't yet fully describe. From this singularity, the universe began to expand rapidly in a process known as cosmic inflation, ballooning in size in a fraction of a second. This initial expansion filled the universe with the incredibly hot, dense plasma required for the formation of the basic building blocks of matter. The Big Bang theory explains not just the distribution of galaxies and cosmic background radiation, but also provides a timeline for the subsequent formation of atoms, stars, and eventually galaxies. This expansion is a critical aspect of the theory because it provides a coherent explanation for the ongoing movement of galaxies away from each other, an observation first noted by Edwin Hubble in the 1920s, which remains a cornerstone of how we measure the expansion of the universe today. Immediately following the Big Bang, the universe was in an extraordinarily hot and dense state, unlike anything we can currently observe directly. During these initial moments, the temperatures were so high that particles of matter and antimatter were being created and annihilated in equal pairs. This period is commonly referred to as the quark epoch, occurring within the first microsecond after the Big Bang. During this epoch, the fundamental constituents of matter, quarks and gluons, were in a state of extreme energy and free from the confines of the particles we recognize today. As the universe rapidly expanded, it began to cool, leading to the Hadron epoch around 1 microsecond after the Big Bang. During this phase, the universe cooled sufficiently for quarks to start combining into hadrons, including protons and neutrons, the building blocks of atomic nuclei. However, the environment was still too hot for these protons and neutrons to bind into stable atomic nuclei. About 1 second after the Big Bang, the universe had expanded and cooled enough to enter the lepton epoch. During this period, leptons, such as electrons, were the dominant form of matter, and the universe was dense with an extremely hot soup of electrons, neutrinos, and photons. It wasn't until approximately 10 seconds post-Big Bang that neutrinos decoupled and began traveling freely through space, no longer interacting significantly with other particles. The period known as nucleosynthesis began roughly 3 minutes after the Big Bang. The universe had cooled to a point where atomic nuclei could form through the fusion of protons and neutrons. During the first few minutes, the majority of the helium in the universe was produced, along with other light elements like deuterium, heavy hydrogen, and traces of lithium and beryllium. This process was largely complete by about 20 minutes after the Big Bang, after which the universe continued to cool and expand, gradually transitioning into the conditions suitable for the formation of atoms, stars, and eventually galaxies. This progression from a nearly incomprehensibly hot and dense point to a state where matter as we understand it could begin to form illustrates the dynamic and violent early history of the universe, setting the stage for all the complex structures we observe in the cosmos today. Quarks play a fundamental role in the formation of matter, particularly in the composition of the atomic nuclei that make up all visible matter in the universe. As the basic building blocks of matter, quarks are elemental particles that combine to form hadrons, which include both protons and neutrons, key components of atomic nuclei. In the early universe, during the quark epoch immediately following the Big Bang, quarks existed in a free state in what is known as a quark-gluon plasma. This was a state of matter where the intense heat and density prevented quarks from binding together. As the universe expanded and cooled, it reached a phase where quarks could no longer exist freely. They began to combine due to the strong nuclear force, mediated by gluons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. For the formation of matter as we know it, particularly in the everyday matter that makes up the world around us, the up and down quarks are the most significant. These 2 types of quarks combine in different configurations to form protons and neutrons. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The protons and neutrons then group together to form atomic nuclei, the heart of an atom. The number of protons in the nucleus determines the element, like hydrogen, helium, carbon, etc., while the number of neutrons can vary within atoms of the same element, resulting in different isotopes. The stability and type of nuclei formed depend crucially on the arrangements and interactions of these quarks within the protons and neutrons. Furthermore, quarks are held together in protons and neutrons by the strong force, one of the 4 fundamental forces in physics. This force is incredibly strong, much stronger than the electromagnetic force that binds electrons to the nucleus, but it acts over a much shorter range. The understanding of how quarks combine and interact not only helps explain the diversity of the elements in the periodic table and their isotopes, but also the processes such as nuclear fusion and fission that power stars and can be harnessed in nuclear reactors. Now, how did the first protons and neutrons combine? Following the conditions necessary for the formation of subatomic particles in the early universe, the process of nuclear fusion emerges as a key concept in understanding how these particles combine to form more complex elements. Nuclear fusion is a reaction in which 2 or more atomic nuclei come close enough to form 1 or more different atomic nuclei and subatomic particles. This process releases a large amount of energy and is responsible for the energy produced by stars, including our Sun. In the core of a star, the conditions of high temperature and pressure are ideal for fusion reactions. For instance, in the Sun, hydrogen nuclei fuse to form helium under temperatures about 15 million degrees Celsius. This high temperature provides the necessary kinetic energy that allows protons to overcome their natural repulsion for each other, due to positive charges repelling, and collide with enough force to combine into a heavier nucleus. As these lighter nuclei fuse into heavier nuclei, mass is not perfectly conserved. Some of the mass of the fusing nuclei is converted into energy, as described by Einstein's equation E equals mc squared. This energy release is crucial not only for sustaining the radiance and heat of stars, but also for the synthesis of elements heavier than hydrogen, which occurs in larger stars or during supernovae events, massive explosions that mark the end of a star's life cycle. Fusion processes in stars are responsible for creating most of the elements found in the universe today, from helium up through iron. Protons and neutrons, collectively known as nucleons, began to combine under the force of the strong nuclear interaction, which is the most powerful force over short distances and acts between all nucleons. At this stage, the universe was still too hot for electrons to be captured into orbits around nuclei, which meant the particles were forming bare nuclei. The first and most fundamental reaction involved a neutron and a proton merging to form a nucleus of heavy hydrogen or deuterium. This reaction is crucial because deuterium serves as a stepping stone in the creation of more complex nuclei. Once deuterium nuclei were available, they could interact with more protons and neutrons to form helium-3 and helium-4. Helium-4 is particularly stable, which made it a common product of these early nuclear reactions. These fusion processes released more energy and allowed further fusion to occur, leading to a slight abundance of helium-4 in the universe, along with trace amounts of other light elements like lithium and beryllium. The specific conditions of temperature and density necessary for these reactions meant that they predominantly occurred during a period called the Big Bang nucleosynthesis, which lasted for about the first 20 minutes of the universe. Building on the nuclear processes that allowed protons and neutrons to combine and form heavier nuclei like helium, the formation of even lighter elements such as lithium involved additional specific nuclear reactions that occurred during the early stages of the universe. These processes were part of what is referred to as Big Bang nucleosynthesis, a series of nuclear reactions that took place within the first 20 minutes of the universe's existence, when it had cooled enough to allow nuclei to form and survive, but was still hot enough for nuclear reactions to occur. After the formation of stable helium nuclei, the process of building lithium began. Lithium, along with beryllium and boron, is considered a light element, and its creation in the early universe was much less efficient compared to hydrogen and helium. The creation of lithium-7, the more stable isotope of lithium, can primarily be traced back to two key processes involving helium nuclei. The most significant reaction for lithium production involved the fusion of two helium-4 nuclei, alpha particles, to form beryllium-8. Beryllium-8 is highly unstable and usually decays back into two helium nuclei. However, in the dense, hot conditions of the early universe, some beryllium-8 nuclei captured another helium-4 nucleus before they could decay, leading to the formation of carbon-12. The process, however, sometimes took a different path where beryllium-8 could capture a neutron and transform into beryllium-9, which could then undergo further reactions to eventually form lithium-7. Another pathway for lithium production involved direct neutron capture by helium-4, forming helium-5, which is unstable and quickly decays into a proton and a tritium, hydrogen-3 nucleus. Tritium could then capture another neutron, becoming helium-4 again, or react with deuterium, hydrogen-2, to form helium-4 and a neutron, with other possible combinations leading gradually to the formation of lithium-7. These processes of creating lithium and other light elements were not as prolific as the production of helium due to the specific conditions required and the relative instability of intermediate products like beryllium-8. As the universe continued to expand and cool, the window for these nuclear reactions closed, freezing the proportions of light elements and setting the stage for the chemical evolution of the cosmos. The recombination era marks a pivotal phase in the early universe, typically dated to about 380,000 years after the Big Bang, when the temperature of the universe cooled to about 3,000 Kelvin. This cooling allowed electrons and protons, which had previously existed in a free state due to the high temperatures, to combine and form neutral hydrogen atoms. This process is known as recombination, although it is slightly a misnomer since it was the first time protons and electrons combined to form hydrogen atoms rather than a recombining of previously combined particles. Before the recombination era, the universe was opaque to most forms of electromagnetic radiation because the free electrons efficiently scattered photons. This period is often referred to as the photon epoch. The high-energy photons, light particles, continuously interacted with the free electrons in a process called Thomson scattering, preventing the universe from being transparent to light. As the universe expanded and cooled, it reached a state where the energy of photons was no longer sufficient to keep hydrogen ionized, where electrons are separated from protons. The density of the universe also decreased, reducing the frequency of photon-electron interactions and allowing photons to travel longer distances without being scattered. This change significantly dropped the probability of an electron absorbing a photon, favoring the formation of neutral atoms. Once neutral hydrogen formed, photons could travel freely without much scattering, leading to the universe becoming transparent to light. This transparency allowed photons to escape, creating what we now observe as the cosmic microwave background radiation, an almost uniform radiation filling the universe, which is a snapshot of the recombination era, providing us with valuable information about the early universe's conditions. Continuing from the recombination era, the cooling and expansion of the universe are closely linked processes governed by the laws of physics acting over cosmic timescales. As the universe expanded from its initial hot, dense state following the Big Bang, it also began to cool. This expansion can be likened to the effect seen when a gas is allowed to expand. It cools down as it does so. The mechanics of this expansion are rooted in the metric expansion of space, which suggests that it is the fabric of space itself that is stretching. This expansion increases the distance between objects not bound by gravity or other forces. As space expands, the energy density of the cosmic material, including radiation and matter, decreases. In particular, the wavelength of radiation stretches, leading to a decrease in its energy. This phenomenon is known as the redshift. For instance, the cosmic microwave background radiation, which was once the heat radiation of a much younger universe, is now observed as microwaves due to this redshift caused by the expansion of the universe. The rate of expansion has not been constant. It is believed that just after the Big Bang, the universe underwent a brief period of very rapid expansion called inflation. During inflation, the universe expanded exponentially within a fraction of a second, smoothing out any irregularities and homogenizing the universe. After this period, the expansion slowed down, governed primarily by the mutual gravitational attraction of all matter in the universe. However, about 5 billion years ago, observations indicate that the expansion of the universe began to accelerate again. This acceleration is attributed to a mysterious component known as dark energy, which seems to constitute about 70% of the total energy density of the universe today. Dark energy, with its negative pressure, is theorized to be responsible for this accelerated expansion as it counteracts the gravitational effects of matter. The cooling of the universe is a direct consequence of this expansion. As the universe expands, the temperature of the radiation filling the universe decreases. This cooling allowed first for the formation of simple atomic nuclei and atoms, and eventually, as the universe cooled further, for the formation of molecules, stars, and galaxies. Following the processes of cooling and expansion in the universe, cosmic microwave background radiation emerges as a critical observational tool for cosmologists. This radiation is the remnant heat left over from the Big Bang, now cooled to very faint microwave light spread throughout the universe. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, CMB provides a snapshot of the universe when it was just 380,000 years old, at which point it had cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms, marking the end of the recombination era. The presence of CMB is one of the key evidences supporting the Big Bang theory. It tells us that the universe was once in a hot, dense state, as the uniformity of the CMB across vast stretches of the sky suggests a common origin for all points in the universe. This radiation is not perfectly uniform. Slight variations, anisotropies, in its temperature provide significant insights into the early universe's conditions, including the density fluctuations that would eventually lead to the formation of galaxies and other large-scale cosmic structures. Regarding atomic formation, the CMB is directly tied to the time when free electrons and protons first combined to form neutral atoms. The process of electron capture reduced the universe's opacity, allowing photons to travel freely rather than being constantly scattered by free electrons. Gravity played a subtle yet profoundly significant role in the formation of atoms, especially as the universe evolved from the simplicity of the Big Bang to the complex structures we observe today. After the cosmic microwave background radiation was released, the universe was primarily filled with a nearly uniform gas of hydrogen and helium atoms. The slight variations in temperature and density of this early gas, hinted at by the anisotropies in the CMB, were crucial for the role of gravity. These slight variations meant that some regions of the universe were denser than others. Gravity began to amplify these irregularities because it more strongly attracted matter where it was already slightly denser. Over time, gravity pulled together these atoms to form gas clouds and eventually stars and galaxies. In these increasingly dense environments, gravity facilitated the accumulation of gas and dust, providing the necessary conditions for the nuclear fusion processes that power stars and lead to the formation of heavier elements beyond hydrogen and helium. In a broader sense, without gravity, the primordial atoms formed during the nucleosynthesis phase shortly after the Big Bang would have remained uniformly distributed across the universe. There would have been no mechanism to clump these atoms together to form stars and galaxies. Therefore, gravity was essential not only in structuring the universe at the macroscopic scale, but also in influencing the environments where atoms could further interact and combine, ultimately leading to the chemical complexity and structural diversity of the cosmos. Following the initial formation of hydrogen and helium in the early universe, the creation of heavier elements is a process primarily occurring within stars through nuclear fusion reactions. This process is called stellar nucleosynthesis, a phenomenon that occurs in the cores of stars as they evolve. In the core of a star, hydrogen nuclei fuse to form helium in a series of nuclear reactions that release a significant amount of energy. This is the process that powers the Sun and other main sequence stars. However, as stars exhaust their hydrogen fuel, they undergo changes that allow for the fusion of heavier elements. For stars much larger than the Sun, once the core's hydrogen is depleted, the increased pressure and temperature from the gravitational collapse allow helium nuclei, alpha particles, to undergo fusion. This process forms heavier elements such as carbon and oxygen in a reaction known as the triple alpha process. The triple alpha process requires temperatures about 100 million degrees Kelvin, which are typical in the cores of red giant stars. The formation of elements heavier than oxygen involves further fusion reactions that can occur in even more massive stars. As the star's core temperature and pressure continue to rise, it can fuse carbon into neon, sodium, and magnesium. This progression continues with the fusion of neon and oxygen and so forth, creating elements up to iron under increasingly high temperatures and pressures. However, elements heavier than iron require a net input of energy to form, which means they cannot be produced through the fusion processes in normal stellar cores. Instead, these heavier elements are synthesized either through the process of neutron capture during later stages of a star's life and in supernovae explosions, which are the violent deaths of massive stars. In supernovae, the intense energy and neutron flux allow for rapid neutron capture by iron seed nuclei, forming heavier elements up to uranium in a process known as the R process, rapid neutron capture process. These heavier elements are then dispersed into space when the star explodes in a supernova. The material ejected into space forms the basis for new stars, planets, and eventually, living organisms. This cosmic recycling and enrichment process enriches the interstellar medium with heavier elements, which are critical for forming planetary systems and life as we know it. How do stars contribute to the formation of new atoms? During the stable period of a star's life, when it is in the main sequence phase, hydrogen atoms in its core fuse to form helium. This fusion process releases a vast amount of energy, which provides the light and heat we receive from stars like our Sun. However, the contribution of stars to the formation of new atoms extends beyond this hydrogen-burning phase. As stars exhaust their hydrogen fuel, they begin to fuse helium into heavier elements. In more massive stars, this process continues sequentially into the creation of carbon, oxygen, and other elements up to iron through fusion under increasingly high pressures and temperatures. This sequence of fusion reactions contributes to the formation of a variety of atoms that make up the periodic table and defines the life cycle of a star. When a massive star has produced iron in its core, further fusion becomes energetically unfavorable, as iron has the highest binding energy per nucleon. At this point, the star can no longer generate the energy needed to counteract its own gravitational collapse. The resultant implosion leads to a supernova, a cataclysmic explosion that is key to the formation of new atoms. During a supernova, the intense environment and the flood of neutrons enable the rapid capture process, allowing the creation of elements heavier than iron. This includes precious metals like gold and uranium, which are formed in these explosive environments. The materials synthesized during a star's life and its explosive death are then expelled into space, enriching the interstellar medium with new atoms. These atoms are incorporated into new star systems, including planets and other celestial bodies. In this way, stars are not only the creators of new atoms through their nuclear processes, but also distributors of these atoms across the galaxy. Telescopes are invaluable tools in the study of atomic formation, offering insights that are fundamental to our understanding of the universe's chemical composition and the physical processes that occur within it. By observing the light from stars, galaxies, and other celestial bodies, telescopes help astronomers decipher the elements present in these objects and the reactions that these elements undergo. The key to understanding atomic formation through telescopes lies in the science of spectroscopy. When light from a celestial body passes through a telescope, it can be split into its constituent colors, forming a spectrum, similar to how light is dispersed by a prism into a rainbow. This spectrum contains lines known as absorption and emission lines, which are unique to each element and act like fingerprints for atoms and molecules. Each element absorbs and emits light at specific wavelengths, and these characteristic lines in a spectrum allow scientists to identify the elements present in a distant star or galaxy. For instance, by studying the spectra from stars, astronomers can determine the abundance of hydrogen, helium, and other heavier elements, providing clues about how these stars have formed and evolved over time. The observation of certain isotopes in stellar spectra can give insights into the nuclear reactions occurring within stars, including those responsible for the synthesis of new elements. This nucleosynthesis, the process by which heavier elements are created within stars from lighter atoms, is a fundamental aspect of stellar evolution. It is also a critical component in the life cycle of galaxies, as these elements are eventually dispersed into space when stars die, seeding future generations of stars and planets. Telescopes equipped with spectroscopic instruments extend these observations beyond our Milky Way to distant galaxies, providing a broader context for understanding the chemical evolution of the universe. By analyzing light from the earliest galaxies and comparing it with light from nearby galaxies, astronomers can trace the progression of atomic formation and the enrichment of the interstellar medium over billions of years. Some of the most significant discoveries about atoms in space have been made possible through the use of advanced telescopes and spectroscopy, revealing insights into the composition and behavior of matter beyond Earth. These discoveries not only deepen our understanding of the universe, but also highlight the fundamental role of atoms in the cosmos. Hydrogen and helium abundance. The most abundant elements in the universe, hydrogen and helium, were primarily formed in the minutes following the Big Bang. Observations of the cosmic microwave background radiation and studies of distant quasars and galaxies have shown that these two elements make up most of the ordinary matter in the universe. This abundance provides key evidence supporting the Big Bang model of cosmology. Heavy elements in stars. Through stellar spectroscopy, astronomers have been able to determine the presence of heavier elements like carbon, nitrogen, oxygen, and iron in the atmospheres of stars. These observations have confirmed that heavier elements are synthesized in the cores of stars through nuclear fusion processes, a theory central to our understanding of stellar evolution and nucleosynthesis. Molecules in interstellar space. Beyond single atoms, spectroscopy has also unveiled the existence of complex molecules in the interstellar medium. Molecules such as water, ammonia, and even organic compounds like methanol have been detected. These discoveries are crucial as they suggest the pathways through which chemical complexity emerges in space, contributing to the formation of planetary systems and potentially life. Isotopic anomalies. Telescopic studies have also revealed isotopic variations in the elements found in space compared to those on Earth. These variations are important for understanding the processes that occurred in the early solar system and are critical for models of how the solar system formed and evolved. Helium-3 and deuterium. These lighter isotopes have been observed in the atmospheres of Jupiter and Saturn and in the interstellar medium. Their distribution helps astronomers understand more about the Big Bang and the processes in the early universe, as their relative abundances are sensitive indicators of the conditions in the first few minutes after the Big Bang. As we delve deeper into the topics of scientific tools, particle accelerators are powerful tools used by physicists to study the fundamental particles and forces of the universe. By simulating conditions similar to those just after the Big Bang, these accelerators provide invaluable insights into the early universe and the building blocks of matter. At the core of how particle accelerators work is the principle of accelerating subatomic particles, such as protons, electrons, and ions, to extremely high energies, and then colliding them at speeds close to the speed of light. These collisions recreate conditions that are otherwise only found in the universe under extreme environments, such as during the first moments after the Big Bang. When these high-energy particles collide, they generate temperatures that are millions of times hotter than the center of the Sun, briefly replicating the hot, dense conditions of the early universe. This environment leads to the formation of a plasma of quarks and gluons, similar to what is thought to have existed during the quark epoch in the first microseconds after the Big Bang. This state is known as quark-gluon plasma, and it is highly significant because it allows researchers to study how quarks and gluons interacted before they coalesced into protons and neutrons. The energy densities and temperatures reached in these collisions cause the quarks and gluons to become deconfined, meaning they are not bound within particles like protons and neutrons, but are free to move independently. This state provides a unique window into understanding the strong force, the fundamental force that holds nuclei together in atoms. Experiments at facilities like the Large Hadron Collider, LHC, at CERN, or the Relativistic Heavy Ion Collider, RHIC, in the United States, use these methods to probe not only the behavior of matter at these high energies, but also to investigate other fundamental questions of physics, such as the asymmetry between matter and antimatter, the properties of fundamental forces, and the nature of dark matter. By analyzing the particles and forces produced in these high-energy collisions, scientists can test predictions of theoretical physics and explore conditions that cannot be replicated by any other means. Going back to atoms, theoretical physicists play an essential role in our understanding of atomic origins by developing models and frameworks that explain how atoms and their constituent parts behave under various conditions. This work is fundamental to bridging the gap between observed phenomena and the underlying principles that govern them, particularly in realms that are beyond the reach of current experimental techniques. At the heart of their work is the development of theories that describe the fundamental forces and particles of nature. For instance, theoretical physicists have elaborated on quantum mechanics and quantum field theory, which are crucial for explaining the behavior of particles at atomic and subatomic levels. These theories help us understand why atoms exhibit certain properties and how they interact with each other and with light. Theoretical physicists delve into the implications of these theories, often predicting new phenomena that have not yet been observed. For example, the prediction of antimatter was purely theoretical before it was confirmed experimentally. Similarly, their work on the fundamental forces of nature, such as the strong and weak nuclear forces, has provided explanations for how nuclei hold together and why certain types of radioactive decay occur. In the context of the early universe, theoretical physicists use their understanding of high-energy particle physics to predict how the universe behaved moments after the Big Bang, leading to the formation of the first atoms. Their models on cosmic inflation, for instance, describe how the universe expanded exponentially in a fraction of a second during its earliest moments, setting the conditions under which matter as we know it could form. Theoretical physicists also collaborate closely with experimental physicists, providing theories that can be tested and refined based on experimental data. For example, theories concerning high-energy particle collisions are tested using particle accelerators, as previously discussed. Feedback from these experiments helps refine theoretical models, ensuring they are accurate and applicable to real-world conditions. Our understanding of atoms has undergone profound changes over the last century. transforming from a simple model of a miniature solar system to a complex quantum mechanical framework that underpins modern chemistry and physics. At the beginning of the 20th century, the prevailing model of the atom, proposed by J.J. Thomson in 1904, was the plum pudding model, where electrons were thought to be embedded within a positively charged sphere. This model was overturned by Ernest Rutherford's gold foil experiment in 1911, which demonstrated that atoms consist of a tiny, dense nucleus surrounded by electrons, changing the way we visualize atoms fundamentally. Following this, Niels Bohr introduced his model in 1913, which incorporated quantum theory to explain why electrons orbit the nucleus without losing energy and spiraling inward. Bohr's model introduced the concept of quantized electron shells, where electrons could only occupy certain allowed orbits with fixed energy levels. This was a significant step forward and matched experimental observations of atomic spectra with great success. The mid-20th century saw further refinements with the development of quantum mechanics, which provided a comprehensive framework for understanding the behavior of electrons in atoms. The Schrödinger equation, formulated in 1926, enabled the calculation of electron probabilities rather than precise locations, introducing the concept of electron clouds and orbitals rather than fixed paths. This model better explained chemical bonding and the properties of atoms that interact to form molecules. In recent decades, our understanding has expanded beyond the electron cloud model, delving into the substructure of the atomic nucleus itself, which is composed of protons and neutrons and governed by the strong nuclear force. We have discovered that protons and neutrons are not fundamental particles, but are made of quarks bound by gluons, as described by the theory of quantum chromodynamics. Experimental and theoretical advances have led to the standard model of particle physics, which not only explains the behavior of known particles, but also predicts the existence of other particles, such as the Higgs boson, discovered in 2012. This model continues to be tested and expanded as we probe conditions that replicate the early universe in particle accelerators, further refining our understanding of atomic and subatomic processes. Quantum mechanics fundamentally reshapes our understanding of atomic behavior by providing a mathematical framework that describes the properties and interactions of atoms at the smallest scales. Unlike classical physics, which predicts exact outcomes based on given inputs, quantum mechanics deals with probabilities and uncertainties. One of the core principles of quantum mechanics is the wave-particle duality, which posits that every particle or quantum entity can be described as both a particle and a wave. This concept is crucial in explaining the behavior of electrons in atoms. Instead of orbiting the nucleus in neat planet-like orbits as earlier models suggested, electrons are described by wave functions that predict a statistical distribution of the positions they may occupy around the nucleus. These are known as electron orbitals. The Schrödinger equation, a key element of quantum mechanics, allows physicists to calculate the wave functions of electrons for a given atomic system. These wave functions do not tell the precise location of an electron at any given time, but rather describe a cloud of probability where the electron is most likely to be found. This approach explains why certain atomic behaviors, such as electron configurations in chemical bonding and the absorption and emission of light, occur in specific quantized, discrete ways. Quantum mechanics also introduces the concept of quantum superposition, where particles exist in all possible states simultaneously until an observation is made. This principle is exemplified in the famous thought experiment known as Schrödinger's cat, where a system can be in multiple states at once until it is observed. Another fundamental aspect of quantum mechanics is the Heisenberg uncertainty principle, which states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. This principle is vital for understanding atomic behavior because it implies that at a subatomic level there is a fundamental limit to what can be known about a particle's location and velocity. This has profound implications for predicting the behavior of electrons in atoms and molecules. Through these concepts, quantum mechanics provides a comprehensive description of how atoms interact, form molecules, and participate in chemical reactions, which classical physics could not adequately explain. Quantum fluctuations are a fundamental concept in quantum mechanics, describing the temporary changes in the amount of energy in a point in space, as prescribed by Werner Heisenberg's uncertainty principle. This principle suggests that it is impossible to simultaneously know with absolute precision both the position and momentum of a particle. One of the remarkable outcomes of this principle is that energy and time are also uncertain to some degree. This uncertainty allows the creation of particle-antiparticle pairs from the vacuum for very short periods of time. These particles and their corresponding antiparticles pop into existence and almost instantaneously annihilate each other, returning the energy borrowed from the vacuum. Although these events are incredibly brief, they are real and have measurable effects, such as the Casimir effect and the Lamb shift. The Casimir effect, for instance, can be observed as a small attractive force between two uncharged parallel plates in a vacuum, caused by the reduction in the number of quantum fluctuations observed between the plates compared to outside them. In the context of cosmology, quantum fluctuations during the inflationary period of the early universe are believed to be the origin of all structure in the universe. Tiny fluctuations in the density of the universe were amplified during inflation, leading to the large-scale structures such as galaxies and clusters of galaxies observed today. Quantum mechanics has significantly advanced our understanding of atomic formation and behavior, yet several unresolved questions remain that continue to challenge physicists and affect our comprehension of atomic and subatomic processes. Addressing these questions is crucial for developing a more complete theory of matter and the universe. Wave function. Collapse. One of the central mysteries in quantum mechanics is the collapse of the wave function. The wave function describes a particle's state in terms of probabilities until it is observed. At the point of observation, it appears to collapse to a specific state. How and why this collapse occurs is not well understood and poses a fundamental question about the nature of reality and measurement in quantum mechanics. Quantum gravity. Understanding gravity in quantum terms remains elusive. The theories of general relativity and quantum mechanics describe the cosmos at large scales and the atomic level, respectively, but they are currently incompatible when it comes to describing gravitational effects at the quantum level. This incompatibility becomes significant when considering the early universe, where quantum effects of gravity would have influenced the formation of the very first particles and atoms. The role of dark matter. Dark matter is known to exert gravitational forces and thus impacts the structure and evolution of the universe. However, its role at the quantum level and its interaction with ordinary matter remain poorly understood. Insights into dark matter could reveal new aspects of atomic formation, particularly in the early universe. Matter-antimatter asymmetry. Quantum mechanics does not fully explain why, following the Big Bang, there is significantly more matter than antimatter in the universe. This asymmetry affects our understanding of the early universe's composition and the fundamental forces that governed the formation of atoms. Quantum entanglement and non-locality. Entanglement, where particles become interconnected such that the state of one, no matter the distance from the other, instantaneously affects the state of another, poses significant questions about information transfer and causality. This phenomenon could have implications for understanding the interactions within early cosmic states where entangled particles may have influenced atomic formation processes. The creation and formation of atoms, from a scientific perspective, are understood through the principles of nuclear physics and cosmology. However, different cultures have their own unique interpretations and mythologies concerning the origin of matter, often weaving these concepts into broader creation myths that provide insights into their worldviews. Western philosophical traditions. The concept of indivisible base units of matter originates with the ancient Greeks, particularly with philosophers like Democritus and Leucippus, who introduced the idea of atomos, meaning uncuttable. This notion was purely philosophical, speculating that everything in the universe was composed of these indivisible units and the void. Hindu cosmology. In Hinduism, the creation of the universe is seen as a cyclic process that includes the creation, destruction, and rebirth of the universe. The ancient texts of Hinduism, like the Vedas and the Upanishads, discuss elements, Panchabhuta, earth, water, fire, air, and ether, which are thought to be the fundamental constituents of the universe. While not directly discussing atoms in the modern sense, these elements can be seen as philosophical equivalents to the basic building blocks of matter. Buddhism. In Buddhist philosophy, particularly in the Abhidharma teachings, there is the concept of dharmas, which can be considered the ultimate constituents of reality. These are not atoms in the physical sense, but are minute phenomena that come together to form the perceived world. The emphasis here is more on the impermanence and interdependence of all entities, rather than a permanent structure like atoms. Indigenous perspectives. Many indigenous cultures around the world, including Native American tribes and Aboriginal Australians, have creation stories that focus on the harmonious interplay of natural forces and entities. While they do not explicitly mention atoms, these stories often describe the universe's formation in terms of elemental forces and the life-giving aspects of the earth and sky, emphasizing balance and unity within the cosmos. Islamic and Middle Eastern views. In Islamic philosophy, particularly during the Islamic Golden Age, scholars like Al-Hazen and Avicenna considered the nature of matter. Though their understanding was influenced by Greek atomism, they often integrated these ideas with theological principles, viewing the continuous creation and organization of atoms as a manifestation of divine order. These diverse cultural views reflect different understandings and interpretations of the universe's fundamental nature. While modern science provides a universal framework for understanding atomic formation based on empirical evidence and mathematical laws, these cultural narratives offer a broader, often more philosophical perspective on the origins and nature of matter, highlighting how different societies have tried to make sense of the world around them. Studying the origins of the universe, particularly through disciplines such as cosmology, astrophysics, and particle physics, involves significant ethical considerations that revolve around the allocation of resources, the environmental impact of extensive research activities, and the broader philosophical and existential questions that such investigations can prompt. One central ethical issue is the allocation of substantial financial and material resources required for high-energy physics experiments, such as those at facilities like CERN's Large Hadron Collider. Critics argue that the enormous investments involved might be more beneficially directed towards solving urgent global challenges like poverty, healthcare, or education. However, supporters of these projects contend that the potential technological and intellectual advancements justify these expenditures due to the long-term benefits they are likely to provide. Additionally, the environmental cost of operating large scientific equipment, which includes significant energy consumption, and the ecological footprint of constructing and maintaining such facilities, poses serious ethical dilemmas. Given the high energy requirements of particle accelerators, for instance, there is a consequential impact on carbon emissions, which necessitates careful consideration and potential mitigation through the use of renewable energy sources. Beyond practical concerns, delving into the cosmic origins can lead to profound philosophical and existential reflections, challenging and potentially altering our understanding of the universe and humanity's place within it. The ethical implications of such knowledge raise questions about existential risks from emerging technologies and the philosophical impacts of discoveries that could fundamentally shift human perspectives on life and our responsibilities to each other. Explorations into the universe's beginnings might also intersect with and challenge cultural and religious beliefs about creation and existence, leading to ethical conflicts about how these subjects are approached in public discourse and educational settings. Balancing respect for diverse viewpoints while promoting scientific literacy requires nuanced and thoughtful engagement. There is an ethical responsibility to consider the implications of today's scientific discoveries on future generations. The knowledge and technologies we develop now can have far-reaching effects, extending well beyond the present day and impacting future humanity and other life forms that might exist or emerge. As our understanding of quantum mechanics and cosmology continues to evolve, future theories about the origin of atoms may likely expand or radically alter our current models, incorporating new discoveries and technological advancements. These future theories might explore deeper connections between quantum field theory, string theory, and unexplored aspects of particle physics, potentially providing a more unified understanding of how atoms and other particles came into existence. Unified field theories. One promising area is the development of a unified field theory, often referred to as a theory of everything, that could seamlessly integrate the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Such a theory might explain how these forces interacted at the very beginning of the universe to produce the first particles, leading to the formation of atoms. Quantum gravity and the early universe. Future theories might also offer new insights into the role of quantum gravity, particularly during the universe's inception, known as the Planck epoch. Understanding gravity at quantum scales could explain how atomic particles behaved under extreme conditions. This could also impact our understanding of space-time fabric and how it influenced particle formation. Another theoretical frontier is the multiverse theory, which posits the existence of multiple, perhaps infinite universes with varying physical laws. Future research could explore how different physical constants in alternate universes might lead to different types of atomic structures or novel forms of matter, expanding our understanding of particle physics in unexpected ways. As the nature of dark matter becomes clearer, future theories may reveal how this mysterious substance influenced the early universe's energy field and contributed to atomic formation. Understanding dark matter's properties could lead to breakthroughs in how we understand the mass and energy that influenced the early stages of the universe. With advancements in particle accelerator technology and observational astronomy, we might be able to simulate and observe conditions closer to the Big Bang more accurately than ever before. These technological innovations could lead to new discoveries about the very first moments of atomic creation, testing the limits of our current models and perhaps necessitating new theoretical frameworks. Dark energy, a mysterious force thought to be accelerating the expansion of the universe, interacts subtly with atomic matter, though its primary effects are seen on the scale of the universe as a whole, rather than at the level of individual atoms. Dark energy is an elusive concept that has puzzled astronomers and physicists since its discovery in the late 1990s through observations of distant supernovae. These observations revealed that the universe was not just expanding, but its expansion was accelerating, a phenomenon that couldn't be explained by existing theories of gravity and cosmology, which predicted that the expansion should be slowing down due to the gravitational pull of matter in the universe. Dark energy is estimated to constitute about 68% of the total energy in the observable universe, yet it remains poorly understood. Unlike dark matter, which interacts with atomic matter through gravity and is thus detectable by its gravitational effects on visible matter in galaxies and clusters, dark energy does not clump or interact with light. Instead, it appears to have a uniform presence throughout space, exerting a repulsive force that influences the rate at which the universe expands. At the atomic level, the direct interaction between dark energy and matter is negligible. Dark energy's influence is primarily gravitational and macroscopic, affecting the fabric of space-time itself. It acts more like a property of space rather than a force acting directly on particles like protons, neutrons, and electrons that make up atoms. However, dark energy plays a crucial role in the large-scale structure of the universe, which indirectly influences the formation of galaxies and clusters of galaxies within which stars and ultimately atomic matter are formed. The precise nature of dark energy is one of the most compelling mysteries in modern physics. It is often modeled as a cosmological constant, a term Albert Einstein originally introduced in his equations of general relativity, which he later regarded as his biggest blunder. Alternatively, some theories suggest it could be a field, similar to the electromagnetic field, with its own dynamics and particles. Further research and new technologies, such as more advanced space telescopes and observatories, are expected to shed light on this profound component of the universe, which, although immensely powerful at cosmic scales, eludes direct detection at the scale of atoms. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. It is estimated to make up about 27% of the universe's mass energy content, significantly more than the ordinary matter that makes up stars, planets, and living organisms. The exact nature of dark matter remains one of the most intriguing mysteries in physics, as it has not been directly observed, and its properties are inferred only from its gravitational influence on visible matter and cosmic structures. Dark matter primarily affects atomic formation indirectly through its influence on the gravitational structure of the universe. It plays a crucial role in the formation of galaxies and large-scale structures. After the Big Bang, the universe was a nearly uniform field of energy and matter, but slight variations in density, quantum fluctuations, became the seeds for structure in the universe. Dark matter, due to its gravitational pull, began to clump around these density fluctuations. This clumping enhanced the gravitational fields, attracting ordinary matter and leading to the formation of stars and galaxies. Without dark matter, the gravitational pull necessary to collapse these regions into galaxies might not have been sufficient, leading to a very different universe. The presence of dark matter created the gravitational wells that guided the ordinary matter to form dense regions where stars and subsequently galaxies could form. Within these galaxies, atomic matter, ordinary matter, continued to evolve, forming new stars and planetary systems. Although dark matter does not interact with atomic matter through the electromagnetic force, which means it does not impact atomic formation processes such as nuclear fusion directly, its gravitational effects were essential in shaping the environments where such processes could occur. By influencing the formation and evolution of galaxies, dark matter provided the necessary conditions for stars to form and for the subsequent synthesis of heavier elements in these stars, which are critical for the diversity of matter observed in the universe today. Antimatter played a significant role in the early universe, especially just after the Big Bang, shaping the fundamental structure and composition of the cosmos we observe today. Antimatter is similar to matter in that it has mass and volume, but its electrical charges are opposite. For instance, where an electron, a particle of matter, has a negative charge, its antimatter counterpart, the positron, has a positive charge. During the first moments after the Big Bang, the universe was extremely hot and dense, filled with a high-energy soup of particles and radiation. In these conditions, both matter and antimatter were created in abundance through processes involving high-energy photons converting their energy into particle-antiparticle pairs, a phenomenon predicted by quantum field theory. This includes pairs like electrons and positrons, protons and antiprotons, and neutrons and antineutrons. According to theoretical predictions and observations of cosmic background radiation and other cosmological data, matter and antimatter should have been created in nearly equal amounts. However, a slight asymmetry favored the creation of matter over antimatter by a very small margin. For every billion pairs of particles and antiparticles, there was one extra particle of matter. This surplus of matter is critical because, as the universe cooled and particles began to combine, matter and antimatter annihilated each other upon contact, releasing energy in the form of photons. If matter and antimatter had been perfectly balanced, this annihilation would have left the universe devoid of any matter to form stars, planets, and galaxies. The reason for this asymmetry remains one of the major unsolved questions in physics and is a focus of ongoing research. Theories suggest mechanisms like CP violation, which proposes differences in the behavior of matter and antimatter, could explain the imbalance. CP violation has been observed in certain subatomic particles at conditions achievable on Earth, providing clues but not a complete answer to the matter-antimatter asymmetry in the early universe. The idea of alternate dimensions affecting atomic behavior is a captivating concept in theoretical physics, largely rooted in the discussions around string theory and other complex theories aimed at unifying the fundamental forces of physics. String theory suggests that what we perceive as particles are actually one-dimensional strings that vibrate at specific frequencies. These strings could potentially extend into more dimensions than the four, three spatial and one temporal, that are part of our everyday experience. The additional dimensions posited by string theory are thought to be compactified, or curled up, at scales so small that they evade current experimental detection, yet they could be integral to the fabric of the universe. In the context of atomic behavior, if string theory or similar multidimensional theories hold true, they might provide explanations for some of the phenomena that the standard model of particle physics can't fully explain, such as why particles have the masses they do, or why the forces of nature are scaled as they are. The behavior of atoms and subatomic particles could be subtly influenced by interactions that occur within these extra dimensions, potentially impacting everything from the fundamental particle's characteristics to the forces governing their interactions. However, as of now, there is no direct experimental evidence to confirm that these extra dimensions exist or affect atomic behavior in a manner that we can currently observe. High-energy physics experiments, such as those conducted at the Large Hadron Collider, have been actively searching for phenomena that could be interpreted as signs of extra dimensions, such as unexplained energy and momentum, which could be leaking into these dimensions during particle collisions. These experiments have not yet provided confirmation of extra dimensions, but continue to push the boundaries of our understanding of particle physics and the universe's structure. Exotic particles, a term generally used to describe particles that don't fit into the traditional particle physics model known as the Standard Model, represent some of the most intriguing and least understood aspects of physics. These particles often exhibit properties or behaviors that challenge existing theories and could potentially reveal new physics that goes beyond our current understanding. One of the most famous types of exotic particles is the tachyon, theoretically predicted but never observed. Tachyons are hypothetical particles that travel faster than light, and if they exist, would have profound implications for theories of relativity and causality. Another example includes magnetic monopoles, which are particles proposed to have a singular magnetic charge, either north or south, unlike normal magnetic dipoles like the common magnet. Although predicted by certain grand unified theories, magnetic monopoles have not been detected empirically. The influence of exotic particles on atomic formation could be significant, particularly if their existence were proven, as they might interact with the fundamental forces of nature in unusual ways. For instance, if magnetic monopoles exist, they could alter electromagnetic fields significantly, which could, in turn, affect the ways atoms and molecules bond and interact. Such changes could potentially lead to the discovery of new types of chemical reactions that are not possible under the current understanding of physics. The presence of exotic particles like tachyons could lead to new models of energy transfer and particle interactions at subatomic levels, potentially offering insights into the early moments of the universe where conventional laws of physics might not apply. These particles could provide clues about the unification of forces and particles in extreme conditions, similar to those experienced shortly after the Big Bang, influencing how atoms and complex molecules might have first formed. Studying atomic formation presents several significant challenges and limitations, largely due to the complex and often elusive nature of the processes and particles involved. One major limitation is the scale at which these processes occur, both in terms of the incredibly small size of atoms and the high energy levels often necessary to investigate them. These factors make direct observation and manipulation of atomic and subatomic particles exceedingly difficult. The instruments required to study atomic formation, such as particle accelerators and powerful telescopes, are not only immensely expensive to build and maintain, but also require a great deal of technical expertise to operate. The Large Hadron Collider, LHC for example, is one of the most sophisticated and costly scientific instruments ever built, and it operates at energy levels that replicate conditions a fraction of a second after the Big Bang. The sheer cost and complexity of such equipment can limit the scope and frequency of experiments. Another significant challenge is the theoretical nature of much of the physics involved. Many theories regarding atomic formation, particularly those extending beyond the standard model of particle physics, remain largely speculative and are often difficult to test empirically. For instance, theories involving dark matter and dark energy, Critical components believed to influence atomic formation in the early universe are constrained by our current inability to detect these substances directly. Researchers rely on indirect observations and the gravitational effects these entities are theorized to have on visible matter, which complicates the study and validation of hypotheses. New theories about atoms have the potential to fundamentally reshape our understanding of science across various disciplines, from chemistry and physics to biology and cosmology. Atoms, the building blocks of matter, have been studied for centuries, and each advancement in our understanding of their structure and behavior has led to significant shifts in scientific thought and technological innovation. If new theories were to emerge that provide deeper insights into atomic structure or introduce new properties of atoms, the implications could be profound. For instance, a new understanding of quantum mechanics could lead to more accurate predictions of atomic interactions, potentially revolutionizing chemistry. This could lead to the development of new materials with unique properties, such as superconductors that operate at room temperature, materials with exceptional hardness or flexibility, or drugs that can be precisely designed to interact with the body at the molecular level. In physics, new atomic theories could impact our understanding of fundamental forces and particles, leading to a more unified theory that could reconcile quantum mechanics with general relativity. Such a theory might offer new insights into the behavior of matter under extreme conditions, such as inside black holes or at the moment of the Big Bang, thus altering our understanding of the universe's origins and its ultimate fate. Furthermore, advancements in our understanding of atomic theory could have practical applications in technology, such as the development of quantum computers. Quantum computing relies on the principles of quantum mechanics to process information in fundamentally different ways than traditional computers. A deeper understanding of atomic interactions and quantum states could accelerate the development of quantum computing technologies, which have the potential to solve problems that are currently intractable for classical computers. In the field of energy, better knowledge of atomic processes could lead to more efficient energy sources. For example, understanding the mechanisms of nuclear fusion, the process that powers the sun, could lead to the development of sustainable and more efficient fusion reactors on Earth, offering a nearly limitless source of clean energy. As we end our journey to uncover how atoms formed from nothing, we realize that we're not just learning about the universe's beginnings, but also exploring deep mysteries about existence itself. This quest into how everything started from an apparent void challenges how we see the world and deepens our understanding of what it means to truly exist. Do you believe atoms and everything we know was created from nothing, or are there other unknown forces involved? Let us know your thoughts in the comments below. Thanks for watching,